so sorry for our. My name is Kazuyoshi Nishijima from Kyoto University. I'm a colleague of Mr. Dr. Yasuda, who made a presentation. And on behalf of him, I say I'm so sorry for the inconvenience that it might cause by this slide presentation. But I hope that you got some interest from our survey, and if you are interested in more specific result information, we are very happy that you contact us. So thank you for listening.
I would like just to make a correction that that speaker was Dr. Tomohiro Yasuda. And I was able to introduce the wrong person. But despite the fact that he's not feeling well, he still pushed through with his presentation. So we would like to thank Dr. Yasuda for that, and also for our audience for your patience and understanding. So
our next speaker got his PhD in wind engineering at the Tokyo Polytechnic University. He's currently working as wind engineer at RWDI and also a lecturer at the UP Institute of Civil Engineering. He's an associate for Asset and UPD-ICE. Ladies and gentlemen, please welcome Dr. RONJIE.COM.
Hello. Parang putol. So good afternoon again. While we're trying to fix the display, so firstly I wanted to mention, so I went with the PICE-JSC joint survey team to Leyte and Samar together with Dr. Eric Cruz and Professor Yasuda and Professor Tajima from the JSC team. And as you can see from their two presentations, our group was split into two. So the presentations from Dr. Eric Cruz and Professor Yasuda focused on survey of the extent of the storm surge. Our group, meanwhile, focused on the wind effects. So it was beneficial to have this joint survey because for us, we would like to know, let's say we see a damaged structure, we are structural engineers by the way, when we see a damaged structure, we want to know if that's water damage, let's say due to storm surge, or wind damage. So we can, let's say our group focused on wind damage, we can say maybe this is wind, or this is water, therefore it's not wind, things like that. So we can separate or clearly identify the effects. Okay, there's like almost done. Yeah. So, parang putol pa rin ito anyway. Anyways, let's try to continue lang. Together with me, as introduced by Dr. Eric Cruz a while ago, William Mata from UPD-ICE, and Justin Valdez. Okay. So as I said, our group is focused on the wind damage survey. I'll tell you about where we went And then one of the objectives of our group was to estimate the wind speed at the site, at the actual site, near the ground. Because as I'll show you later, there are different wind speed estimates, but they're not actual wind speed estimates on the ground at the peak of the typhoon. And then of course I'll show you some example damages and summarize everything. In addition to our group, of course, as Dr. Eric Cruz also introduced earlier, Engineer Briones also came with us, Engineer Ortigas as well, part of the organizing local coordination with us. But Engineer Briones, particularly, aside from being a DPWH engineer, he's also a member of ASEP, actually an officer of ASEP, Association of Structural Engineers of the Philippines. So, and of course, as I said, we went with the JSE survey team, which focused on storm surges. So as also mentioned earlier, we were on site from December 12 to 16, and that's just to point out that's already more than 1 month after the event. So there was a lot of things that we didn't see anymore because there was some cleanup already done and some reconstruction already for some houses and so on. But on the first day when we arrived, we just did a drive around Tacloban and just, if you've been there, if you went there for the first time after the typhoon, you'll just be overwhelmed. So we thought there was just too much to see, too much to document, too many damages. And so on day 2, while the storm surge team went to eastern Samar, Gian and Giwan and that part of Samar, we decided to focus instead on Palo, Leyte, which is just south of Tacloban, where the storm surge effects are actually there's little effects from storm surge. So most of the damages there are due to wind. Then on day 3, we went with one of the storm surge teams to visit parts of Samar, and then day 4 just concentrated again around Palo and Tacloban, and actually south of Tacloban, further south of Tacloban, closer to the path of the storm. So for example, if this is the path of Yolanda, Typhoon Yolanda, this is Tacloban, the airport is somewhere here, Palo is somewhere here. We went as far south as Dulag, so this is Tolosa and Tanawan, Leyte. In Samar, we went as far east as Balamiga, part of western Samar already, and then Osmeña, Marabut, and I think Lawaan around this area. So as I was saying earlier, there are different reported wind speeds. For example, the Joint Typhoon Warning Center said they estimated, so it just estimated 350 kilometers per hour, 1 minute sustained winds, converted presumably over ocean, over open water. So on land, that's the gust speed over land. The JMA, also of course, Japan Meteorological Agency, estimated 10-minute mean speeds, 10-minute sustained winds of around 230 to 35 kilometers per hour. So in terms of on-land gust speeds, that's around 270 kilometers per hour. The New York Times, if you visited their website about Typhoon Yolanda, they're saying just 190 kilometers per hour, approximately. So these are all converted numbers because they're not exactly measuring gust speeds on land, which we are concerned with as civil and structural engineers. But I should note, when we say 300, let's just say Leyte, Tacloban experienced 315 kilometers per hour. That's actually already a 7,500 year approximate return period gust wind speed based on the current models we have. So it's rather a very rare wind event. Just FYI, if you're not aware, in the National Structural Code of the Philippines, Leyte is currently assigned a 50-year gust speed of 200 kilometers per hour, and additional FYI. So basically, we expect some damage or inelastic structural response already only when the wind speed is beyond 250 kilometers per hour. So definitely, if we're expecting, let's say, more than 250 kilometers per hour, let's say 300, 350, that will be, you expect structural damage. So and that corresponds to 250 corresponds to 700-year return periods. Meanwhile, in Samar, it's the 50-year gust speed is design gust speed is 250 kilometers per hour, and the 700-year return period gust speed, where damage will start to occur, is 315 kilometers per hour, so close to that number. But so one of the things we did was look for simple structures where, based on their strength, an estimate of their strength, we can back calculate the wind speed experienced at the site. So at Lawa and Samar, we saw this actually light post. So tubular steel, around 2-3 meters high. It was bent. Actually, we're not sure if it was because of flying debris or if it was because of the wind. In fact, so here you can see it is bent towards the right, and meanwhile the sea is somewhere there, so it's suggesting winds coming from the land, inland. So actually northerly winds must have affected it. Just based on what we know, let's say for a shape, cylindrical shape, wind force coefficient might be somewhere around, let's say, as high as maybe 1.4. And then it depends on the terrain, surrounding terrain. Whatever you assume, you can assume suburban terrain, which is the case here. But we also assume, let's say, to get somewhere close to 350 kilometers per hour, we have to assume open terrain, which is actually not the case, although for a relatively small structure and you have damage, let's say adjacent to it, there's a damaged house, collapsed house, maybe it will, it's an acceptable assumption. But these are all assumptions. But it seems, based on this, our estimated strength of this pole, we can only say maybe it is higher. The actual wind speed, at least at this location in Samar, might be higher than 350 kilometers per hour gust speed on land. And so to show you some examples of damages, we looked at public buildings, schools. This is UP School of Health Sciences in Palo. Of course, there's the oblation, a symbol of the University of the Philippines, if you're not aware, still standing, but the relatively older building adjacent near it, mostly timber construction, timber walls, so there's severe damage to the roof. And usually what happens is if you have damage to the roof, you have damage to the contents of the building inside. But what also happened here is there are some damages to the windows. And this is pretty much the story of the damages to schools. So typically it's one-story buildings, concrete walls, in this case, in most cases, and then steel roof sheets, usually on timber roof trusses. Same case here, although I also wanted to show this because you can see here you have two adjacent buildings, same location, same site. One has severely damaged roof. The adjacent one doesn't have as bad damages. So it's because of the complex nature of wind. It is possible that something's providing some shielding effect and so on, or maybe there's some wing effect. Let's say the wind is coming from here because it's based on the direction of the coconut leaves. So there could be some wake effects that sort of channel or funnel the wind to affect this more and so on. So actually it's very complicated. It depends a lot on the surrounding terrain. But here, this one is in Samar. Typical, of course, of our school buildings, one-story buildings, is the use of very large windows. of course, for ventilation purposes when there's no storm. But the problem is when there's a storm, usually they're not protected, or basically they're open, and so that whether they're open or they're closed, but they have, let's say, glasses that are not designed to withstand wind pressures, the glasses might break, and then wind pressure will go inside the building and provide additional uplift force on the roof. So sometimes or often it's always important to cover or provide protection for the windows during a storm only, so that might lessen the impact of wind on the roof. So just to repeat again, usually on the roof you have suction forces due to wind, but in addition to that, you could have internal pressures that, in addition to the suction from the top, there's a pushing pressure from the bottom, from the inside of the building. So, but anyway, this is our typical construction in the schools, especially of course in outside of Metro Manila. Here in Metro Manila, we have multi-story buildings already. But here is another case on this actually there was a building here, it's not there anymore. And here you can see, you can see the direction of the wind based on the coconut trees. And there, again, one-story building, timber roof trusses, roof frame, blown off roof sheets. Same story. Although here I noted this is in Tanawan. There's also the effect of storm surge, so it's combined water and wind effects already. That's why you have more severe damage to the main structural frames. Hospitals, more or less the same story. In this case, we have a two-story building. Part of it has steel roof trusses. The roof sheets were blown off, but at least the steel roof trusses are still there. Although again, there's some damage to the second floor of the building. I mean, the contents of the second floor, so because of the blown off roof. Same location, you have again similar story to the school buildings. One-story building, timber roof frames, damaged interiors, and then some damage to the, of course, to the timber roof trusses. And you can also see there's essentially it doesn't act like a diaphragm system. So same case here. We observed also that the connections sometimes might be the issue. Although in this case, of course, it didn't. It stayed there, but anyway, the roof sheets were blown off. This is BIR District Office building. Actually, you might not think of it, but there used to be large glass windows here. They're all gone. And you can also see the roof sheets have been blown off, although the steel roof frames are still there. Again, I think what might have caused this are the breakage of the windows and then additional roof pressures from inside. At the airport, Doc Cruz earlier presenters showed some damage to the terminal building, to the airport control towers building. Actually, there are some damaged windows, and based on interviews, they said that all of the glasses here were actually broken, and then they just replaced it. So that's why there's new windows on the control floor itself. This is another actually office of Senior Citizen Affairs office building in Palo Leyte. So blown off roofs, actually in this case rather small sized roof trusses, roof framing. And if you can see here, there's no more, it looks like there's no more wall on the left side of the buildings because the walls also were blown off. Apparently they used just 4-inch CHB or concrete hollow block walls there, so not which is usually we use 6 inches for exterior walls. For residential buildings, so same case. Of course, we have plenty of roof damages. Here again, you have a relatively old building with timber trusses. So the timber, aside from the roof sheets, the timber trusses themselves are damaged. Here, the steel roof framing is still pretty much intact. The roof sheets are the only ones damaged in the newer building. This is one example of very old type of construction. It's actually it was a two-story building. The first floor is mostly has concrete walls, and then you have a wooden second floor and then this is just one example. We've seen many others, but the whole second floor was damaged. And again, just to point out, this is actually Palo Leyte. The water did not reach this area. It's clearly wind effects that just damaged this building. And again, so it damaged the second floor. The second floor collapsed on the first floor, so you have, of course, property damage there. Now they just put some temporary roofing on the first floor, so they're still able to live there again. And of course, falling and flying debris could be a problem. This is just one example. We're not sure, but it's possible that the roof sheet was blown off, then it hit the tree fell down, and damaged, well in this case just the fence. I think it didn't reach the house, but if you could just imagine, but I mean in previous storms this has happened, many trees falling on top of adjacent houses. And then this is one house where you can see that they have a roof there. They have already actually reconstructed their roof, but basically the same way as they have it before. You have very light timber framing and then steel roof sheets. But so I guess it's economically it's okay, because if you're just talking about 7,500 year winds, then maybe it's still okay. I mean, not for building code compliance, but anyway, just to mention to you too, based on our interviews with the people living here, there used to be 2 other buildings adjacent to it, but they're now gone. They're not there anymore. Sorry, this is a very, not very clear picture, but of course, there were plenty of coconut trees, especially around Leyte, and a lot of them fell down. They're a source of livelihood for many people there. Well, in this case, actually, the trees, so we went up a hill, this is in Palo, the trees fell southward, suggesting northerly winds, or winds coming from the north blowing south, which suggests that even before the typhoon made landfall, so a few hundred meters away from the coastline, let's say the eye of the storm is there, you have your winds inland or on land are blowing from north to south. So even not yet at the peak of the storm, you already have very strong winds. Steel lattice towers, this is just an example of an antenna tower which collapsed. But surprisingly, just a few hundred meters away, there's another lattice tower. A different configuration, of course, but it's on top of a hill, but it's still standing. Actually, yeah. So again, because wind is a very complex phenomenon, but basically, of course, we don't design for 7,500 year winds, but we observe here it's just the sizes of let's say the elements of this structure are just not strong enough, because again, it's a very strong storm, and it appears there's no problems with the connections in this case. And then you can also imagine open steel roof structures. So for example, this used to be a basketball court. There used to be a basketball backboard and ring there. So that got blown away. But actually, this roof, steel lattice roof structure used to span on top of that basically on top of this court, open court. But it got lifted up and it got tossed to the side. And it got lifted up and because basically the damage occurred at the connection at the base. So in this case, you can see the connection detailing. Yeah, you have welded angle bars to the main truss, the vertical truss and the base plate and so on. So, well, at least again for let's say these very strong winds, it appears insufficient. And in many cases, this is the connection detail they use. You have let's say concrete structure, a concrete column or pier, and then they just extend the rebar from the concrete column to hook the roof trusses. In this case, this main truss didn't fail, but you can see there used to be a truss line here, which was lifted off from the support. And then walls also. I think in typical structural design practice, we design roofs for wind, but not walls. So in this case, at least it appears, we're not sure because again we were there a month later. The roof was blown off, but there's also some wind effect on the wall itself. I don't know if you can see it, but the wall tilted a bit to the left. And then again, wall roof systems. So you have so this is one example, is an auditorium structure. So you can basically large open space. This is another example, large open space. You have steel roof frames, and then concrete supporting structures, columns and walls. So actually this is relatively new construction, maybe not more than 5 years old, but you can see extensive damage to this structure. I think, of course, there's obviously some the truss might have been lifted off its support, but at the same time, the walls themselves carried a little bit of the forces and the loads, and of course they're not usually designed to do that. Another close-up view of the very large walls. This is around 15 meters to 20 meters tall. Yeah. So just to summarize, again, wind is a very complex phenomenon. We know that already, but we can, like windows or glass curtain walls, they're not usually protected or they're not usually designed. There are no shutters, no boarding up. We don't usually do that. Lightweight steel roof sheets damage, usually timber roof frames as well. Because of these, there's also damage to, if you have a damaged roof, you will have damaged interior contents of the sheltered floor. Then sometimes it's inadequate structural connections. Sometimes it's certain elements of the structure that are not typically designed to carry wind loads might need to be considered. And then there are very old buildings that are not yet upgraded. And then of course there's falling non-structural hazards. And then we notice that people are reconstructing the same way as before the storm, which might be an issue, maybe not. Just as a last slide, some unsolicited suggestions or ideas. So obviously, if possible, we need to protect windows. Maybe that could help relieve some pressure off the roofs, wind pressures off the roof. I'm also thinking, I didn't see any, basically the concrete roof slabs that I've seen, roof deck slabs, they're still there, of course. So if you can use concrete roof deck slabs instead of steel roof sheets, of course, that would be good for wind. Of course, you have to design the whole structure sufficient for earthquakes because that's a heavy mass. If we can avoid timber, of course, because they're very light. unless of course you can demonstrate by testing or analysis it is sufficient. And then again, basically we need to check all elements exposed to wind. So again, at least even in my own experience, I've usually just, let's say for small structures, 2-story building maybe, I just check the roof for wind, but not all the other parts. And then, because we didn't see any code compliant structure, we can't say that there's a need to update the current wind resistant design standard, the 2010 National Structural Code of the Philippines. So I think as long as I think the implementation of the standard, our current design standard, is one of the first things we can do. So that's all for my presentation. Thank you very much.
Thank you very much, Dr. Amilo. At this point in time, we invite all 5 speakers to go on stage for the